going to go through some calculations for what you might see in astronomy, right, for this chapter 3 stuff. And so we're talking about Kepler's laws. So there's two things that we're going to do. One is Kepler's third law. And the other thing we're going to do is perihelion and aphelion. And this has to do with eccentricity. All right, and so the idea for eccentricity is if we have an ellipse, we have our normal idea, the semi-major axis there. That's kind of our radius for the ellipse. But we also have, right, we have two foci in the ellipse. And those have distances c. And so we can define the eccentricity as c over a. Now, if this is the sun over here on the right, then this distance here has to be c minus a. And we can write that in terms of eccentricity. And so if we want, we can say the perihelion, the closest distance, well, that's c minus a. But c is, let me write it down here, c is a times the eccentricity. So this ends up being, sorry, it's not c minus a, it's a minus c. You gotta be careful of that. So we'll have a minus a times eccentricity. And so this ends up being the semi-major axis times 1 minus e, 1 minus the eccentricity. And that makes sense. This is going to be a number that's between 0 and 1, and the larger the eccentricity, the smaller this is, and the smaller the total distance is. So we can do the same thing. The aphelion, the farthest point over here, should be a plus c. So but that is a plus, well, c is a times e. So this is a 1 plus e. And that should make sense that it's the far distance. So we'll call these peri and ap. Right. So we want to start out with some planets, and we want to calculate based on what numbers we know, the stuff we don't know. And then we can figure out their, we can figure out the information that we need. So let's look at Venus. Now, so what I'm doing is I'm looking straight at the data tables on page A15 in your appendix of the book. All right, so for Venus, we can look and we can say that the period is 0.6152 years. All right, what we want to know is what is A. Well, we can get that directly from Kepler's third law. Right, so we have p squared is a cubed. So a must be the third root of p squared. So you have to be careful of that. That means you have to know how to calculate it at some point. So our average distance, our semi-major axis, is going to be the third root of 0.6152 squared. Calculator on 0.6152. We square it. That makes sense. Now we got to figure out how to take this third root. And usually you have some key here that lets you do it in some way. You need to make sure you know how to do that on your calculator. This is why you keep the manual to your calculator. But for me, it is 1 divided by 3. And we used that exponent button to put the exponent there. And this is 0.723. And this is an engineering formula, is you have to put in years on one side and get AU out on the other. So we get 0.723 AU. When we look it up, it's 0.723 AU. That's good. Now we can go and say, well, what is the closest and the furthest away it gets? And that means we need the eccentricity. So E here, if we look it up, is 0.007. That means the closest it gets is Perry is A1 minus E. And that is 0.723 AU times 1 minus 0.007. Yeah, that's right. 3 zeros. Yeah. Oddly, Venus's orbit is fairly circular. When you look at these, it's probably the most circular, so this is not a great one to calculate on, but oh well. We can calculate this. This is 1 minus 0.007, and we get 0.718 AU. And we can go and calculate what AP is. It is A1 plus E. And it's 0.7323 times 1 plus 0.007. So we'll calculate that. 1 plus 0.007. And we get 0.728 AU. Okay. There we go. That's all in the picture now. So those are the kinds of calculations you might be expected. Now, you could, in principle, invert this. You can ask, well, what is eccentricity in terms of these other things? And if you wanted to do that, I'm just going to lay out how to do it. You essentially have two equations. X is A1 minus E, and Y is A1 plus E. So you want to solve for E. In terms of these things. And we would like to get rid of A here if we could. So maybe solve for A. A is your semi-major axis. And so it is X divided by 1 minus E. And so Y is X over 1 minus E times 1 plus E. All right. Okay, and so there are some tricks. You do Y 1 minus E is X 1 plus E. And so you can rearrange this Y minus YE equals X plus XE. And so eventually what we'll get is Y minus X is Y plus X E. So you can find the eccentricity is, so Y was the aphelion. And so you can write it eventually like this, if you would like. It is possible to solve it. We saw what I had to do to solve it once, and honestly, the form of the equations that we want you to deal with is this. Because what you're going to do is measure kind of, take an average of these two, not necessarily go and try to figure out the eccentricity, but you figure out A just from taking the average of these measurements and use that to find the eccentricity. So let's do a calculation in the other direction. We'll look at mercury. So we're trying to get through these fairly quick. All right, and the distance for mercury is 0.387 AU. We want to know what the period is. Right. Well, we have P squared is A cubed, so P is the square root of A cubed. Right. And so we can just plug in. P is the square root of 0.387 AU squared. Now we ignore the units because this is, again, you have to put in years for the period and astronomical units for the distance. But we'll do, and this is cubed there. So 0.387, and then we have to use button to get cubed. Oh, something went wrong there. 0.387 cubed. Okay, that's fine. And we take the square root of that. Period is 0.241 years. And when I go look that up in the text, mercury's period is 0.2409 instead of 0.24075. Close enough. Mercury is a little bit weird. It has a high eccentricity comparatively to the planets, and it is the most affected by gravitational pulls from the other planets. Its orbit isn't perfectly elliptical. We'll talk about that in chapter 4. Now, if you get this and you want to express it in other terms, you're going to have to do a unit conversion. P is 0.241 years. Let's say we want it in days. We have to multiply. We want years on the bottom, so it's times 365.25 days. And so if we do that times 365.25, we get 87.9 days, which is probably what normally it's at, about 88 days for the orbit. All right. Now, as we go on, when we start doing, in physics, start doing this calculation for things that don't orbit the sun, your units are going to change here, and that means you're going to have to know your unit conversions and be careful of those. But I think that's enough for here. So I hope y'all are enjoying this or at least getting something out of it.